really glad to be back here in Berlin. I believe I gave my first conference talk in this very room 6 years ago. And since then, I've been at every meeting C++ that happened in Berlin, so it's really good to be back. I'm here to talk about a deep dive into dispatching techniques. This is a talk about performance, so I need to start with the following disclaimer. You should never optimize without running your own benchmarks. And just because I'm going to present you some benchmark results in this talk, don't just copy them blindly and say, well, he measured this, he said it's good, so I'm just going to use this technique. Run your own benchmarks on your own hardware. All my benchmarks are on a 2020 Apple Mac Mini with the M1 processor running as Linux and Clang 14. This is most likely not the exact configuration you're targeting, so it's important, run your own benchmarks, verify the technique, and then make a choice. So I'm here to be talking about optimizing dispatching, and at the core is this dispatch loop. So the pattern is we have a while loop, and inside the while loop we have a switch. So we repeatedly need to decide between different cases and need to execute different code. So this is an example of a dispatch loop. We want to pass a binary file. So it consists of headers and payload, so we repeatedly pass a header, then we switch over its type, and depending on the type, we pass different things. This is not an example of a dispatch loop because it's no loop, right? We just convert an enum to a string. This is most likely not going to be performance-sensitive code. If your entire runtime is spent doing enum to string conversion, something's gone really wrong. And of course, we've got the canonical example of a dispatch loop, a bytecode interpreter. We've got a sequence of instructions that we want to execute. And this is also the example that I'm focusing on in this talk. So let's define a simple bytecode that we then write an interpreter for it and benchmark various dispatching implementations. So the bytecode is very simple. It's a simple stack-based bytecode. And each instruction, like the opcode, is 1 byte. This is where the name bytecode comes from. So we've got an opcode, which is the enum. This is what we're going to switch over. And then an instruction is a sequence of either opcodes, values, or offsets. So the idea is that we've got an opcode, and then based on the opcode, we might have multiple values following it. And then we execute different things, use them in the execution of our instruction. The bytecode is stack-based, which means that the operands aren't specified as part of the instructions. There is a value stack, or vstack for short. This is similar to our Wasm-Works, if you're familiar with that. So we have, for example, a push instruction, which pushes a constant onto the stack. So we've got ABC, and then we push 42, and then we've got ABC 42 on the vstack. And that constant is specified in the byte afterwards. So we've got 1 byte that contains the push opcode, and then the next byte contains 42. And this is then pushed. To add to values, we again use the vstack, so we pop 2 values, add them, and push the sum back. So we modify them on the stack. And with that, we can write a simple program that adds 2 numbers. So we push our first 2 numbers onto the vstack, then we call add, which pops them and pushes the sum again. Then we can push the next number, call add, and then we have the result on the vstack. Of course, as we can see, this is a bit limited. For example, every time we want to use a value, we pop it from the vstack and can't reuse it again. So we want to use the same value multiple times. What do? We need an instruction for that duplicates the top value. So the dupe instruction simply duplicates the value that's on top of the vstack, and then we can use it multiple times. Similarly, the stack might be in the wrong order, so we need to clean it up. And for that, we might need to swap 2 values. So if you've got the instruction swap, it swaps 2 values that are on top of the vstack. All the instructions so far, they just happen sequentially. This is maintained using an instruction pointer, or IP for short. So this is simply it points to the next opcode in our bytecode. And then after we finished executing a normal instruction, it simply increments the IP past the opcode plus any data of that instruction. And we can also implement jumps to go loops and branches like with that approach. So a jump instruction increments the instruction pointer by the offset, which is specified in the next byte. So that way we can jump to an arbitrary place in our program and implement loops, for example. So we want to jump back to the beginning of a loop. And then we've got a conditional jump to implement if statements. This only increments the instruction pointer if the top byte is non-zero. Finally, we want to add a function calls, and for simplicity, we only consider a single function. So the entire bytecode is the body of our function. The arguments for that function are pushed on the vstack before we start executing. So what is on the vstack, those are the arguments, and then the return value is what's left when we're done executing. Then we have a call instruction, which only calls the current function. So it's really a recurse instruction, and it simply jumps back to the beginning of the bytecode. But before it can do that, it needs to save the instruction pointer so that the return instruction knows where to jump back. So return jumps back to the previously saved location, and they are saved on a call stack. So we've got a separate stack that contains the instruction pointers. And with that, we can write the following function that computes recursive Fibonacci. So the first line is the pseudocode. That's what we're doing, the very straightforward recursive implementation of Fibonacci, which is really slow, but that's not important. And then the bytecode. So the function starts with n on the v-stack, and we want to compute the n Fibonacci number. For that, we need to compare it against 2, but this would consume it, so we duplicate it. So we duplicate n, push 2, and compare it. If it's greater than or equal, we jump to the bottom code. Otherwise, we continue on. So if it's less than 2, which means this means that n is already the n Fibonacci number, and we can immediately return. Otherwise, we need to subtract 1. This would again consume n, so we duplicate it. Then we can subtract 1, recurse. Recurse will jump back to the beginning and compute it recursively for the n-1 Fibonacci number. When that returns, fib n-1 is on top of the v-stack. We then want to compute the n-2 number. So we first need to swap them so that now n is on top of the stack. Then we can subtract 2, and then we can recurse. Finally, we've got fib n-1 and fib n-2 on the v-stack. We can add them, and we can return that result. You don't need to follow the exact details. The code works. I've tested it. But just conceptually, do you understand what's going on here, how the bytecode works? OK. Now let's implement an interpreter for that. For that, we need to maintain four things. The instruction pointer, which points to the current opcode. The v-stack pointer, which points to the top of the v-stack. The c-stack pointer, which points to the top of the call stack. And then finally, bytecode itself, so we know when we recurse, we can jump back to its beginning. And then each implementation is just a couple lines of C++ code. So when we push something, we read the value in the next byte after the opcode and push that on top of the v-stack. Then we increment it by 2 to skip past the opcode and the value. To duplicate the top value, so v-stack always points at the location where we are next going to write a value. So the top value is at v-stack -1. So we get that and push it again. So now we've duplicated the top value, and then we increment the instruction pointer. To add two values, we pop them, compute the sum, and push the sum, and increment. Conditional jump looks at the top value to determine whether it's non-zero. If it is non-zero, we jump by incrementing the instruction pointer by the offset in the next byte. Otherwise, we skip past it by incrementing by 2. A function call simply pushes the instruction pointer, or rather the instruction pointer +1, because that's the location where we want to continue after the call. We don't want to call again. This would be an infinite loop. And then we jump back to the beginning of the bytecode. And finally, return simply goes to the location that we last saved. Then we can write a function that executes bytecode. So it takes bytecode and the argument. It sets up the v-stack and call stack. So the call stack starts with an exit instruction. This is just a dummy instruction, so we're done executing. And that way, the first return jumps to the exit instruction. Then we know we're done and can finish the interpreter loop. And the v-stack starts with the argument. And then we just start executing the bytecode by calling dispatch. And this is really the missing piece of code. So dispatch takes the interpreter state, and its job is to read the current opcode, execute the appropriate piece of code that I've shown you a couple slides ago, depending on the opcode. This also increments the IP, and then we repeat that in a loop. And so for the remainder of this talk, we're only going to implement this function in various different ways and measure it. But before we do that, a quick disclaimer. Bytecode interpreters are prime candidates for remote code execution exploits. Right? So you should never start executing untrusted, unverified bytecode that somebody just gave you. It can do arbitrary things. It might escape your sandbox. Right? This is a security vulnerability. This is a talk about performance, so let's ignore that. And start with the most basic dispatch implementation, the switch statement. Right? We've got a loop, an infinite loop. We switch over the current opcode. For each case, we just insert the C++ statements I've shown you a couple slides ago. The exit instruction, it simply breaks from the loop and returns the return value. And then we're also marking the compiler that these are all the instructions that we care about. So don't assume that any other value can exist. So I've now shown you, spread over multiple slides, the complete interpretation of the interpreter. If you don't know in full detail what it does, don't worry, just pause the YouTube video, go to the end of the slide, I'll share a link to the full source code. Sorry, you have you can't do that here. OK, so to get a feeling for the performance, we're going to look at the generated assembly code. Who here can read assembly code? OK. Who here thought I was referring to x86 assembly code when answering that question? OK, I'm going to look at assembly code in 64-bit ARM, but don't worry, it's actually easier to understand because it doesn't pretend to be a CPU from the 70s. So ARM has 31 registers. They are labeled 0 to 30. quite reasonably. If they have an X prefix, they're 64 bits, so this is a 64-bit ARM architecture. And with the W prefix, you get the lower 32 bits. But it's otherwise the same register. And then quickly the addressing modes that we so it's about dereferencing a register. When you have a register that stores a pointer, you can dereference it directly or by an offset, so add an offset before dereferencing it. You can also combine the offset with an increment, and you can either increment it before you dereference it or after. So you increment it and then get the address, or you get the address and then you increment it, like in one instruction. And finally, for array indexes, you want to index it with another register. So this, we have got a base address at x0. We add the index in x1, shift it by 3, and get the value back. This is useful for array addresses. But don't worry, all assembly code is annotated. So this is the assembly code generated for the switch statement. We've got a label for a loop, and then we load the opcode. So we load 1 byte. x0 is always going to be the register that contains the instruction pointer. So we're loading the current opcode, storing it in a register, and then we compare it. So we first compare it against 0. This checks, is the current opcode push? If so, we jump to the push label. Otherwise, we continue, compare it against the add instruction, jump to add, and so on, until we finally have an unconditional jump to the exit instruction. This is because we told the compiler that there are now more values left. Then the push instruction generates essentially like straightforward assembly code for the C++ instruction. So we load the value that we're pushing, we are storing it on the VStack with an increment, incrementing the instruction pointer, and jumping back to the loop. Very straightforward. What we're essentially doing is we're getting the opcode, comparing it against each possible value, and jumping to the appropriate label. This is a linear search. But the actual labels themselves, they're sorted. And if you want to find something in a sorted sequence, there's a faster algorithm, binary search. And actually, Clang generates binary search. So the actual generated assembly looks something like this. It's a bit tricky to understand in assembly code, so here's pseudocode. So we're checking, is the instruction pointer between 0 and 3? If so, we know that we're in that half, then we do, like it's a binary search. And this simplifies, like reduces the number of comparisons that we need to make until we figure out where to jump. So good job, compiler, there. Of course, it's completely meaningless just to look at assembly, so let's measure it. And for that, we can use the recursive Fibonacci implementation because it's really good because it has exponential blowup. So with just a few bits of bytecodes, we can, because it like calls itself twice in each iteration, we get more and more bytecode and can easily execute like millions of instructions to get like really long times that we can good benchmark. So we compute the 35th Fibonacci number and get this result. If you can't read the number, don't worry, it's about 460 milliseconds. Now, who thinks that is fast? 460 milliseconds to compute the 35th Fibonacci number. Who thinks that number is completely meaningless without any context? Exactly. So, how to benchmark? You need to take multiple runs because of noise. Then you need to report the averages and standard deviation, none of which I did. And then you need to compare it against some alternative implementation. This is a bit tricky, but luckily there's a really great command line tool that you can use, Hyperfine. So Hyperfine can be used to benchmark command line applications. It will run them repeatedly, gives you the average and standard deviation, the entire execution range, and then at the end gives you a summary of which one is the fastest. I highly recommend you get it. It's one of those suite of modern written in Rust command line tools that are really useful. So just for the sake of argument, since we don't have an alternative implementation yet, let's just assume it's too slow and we want to optimize it. So how to optimize? Step one is we need to guess what could be a problem. Right? This can be an educated guess or just a wild speculation. Like, we need to guess something that we want to dig deeper. And my guess here is that we have got a problem with the branch predictor. So what do I mean by that? The actual assembly instruction on the CPU, this is very simplified, happens in phases. So for example, we first need to fetch the memory for the instruction. Then we need to decode it and figure out what it does. This is essentially a dispatch loop built in the CPU. So we need to figure out what the instruction is, then we execute it, and then we can write the results back. And because all of those steps happen on different parts of the CPU, we can actually execute them in parallel. So this forms the instruction pipeline, and the idea is that while we are executing one instruction, we can already fetch the next one in parallel to get reduced latency. Of course, this has an issue with branches, right? When you have a branch instruction, we don't know what's the next instruction going to be. It can be one of multiple locations. So what does the CPU do? It simply guesses, right? It guesses whether the branch is taken or not, and just starts executing its guess. If it's correct, good job, we made efficient use of the pipeline. If it's incorrect, and it started executing something that it wasn't supposed to execute, it has to clear the pipeline, roll back. This is expensive. So we want to guess correctly. This is where the branch predictor comes in. We sort of remember like a history of in the past, this branch was always taken, so we guess it's taken and start executing it. That way we can make a good prediction and make use of the CPU pipeline. But in our case, we're executing different instructions in every loop iteration, right? So it can't guess whether or not a branch is taken, because every loop iteration we're taking, like doing something completely different. The branch predictor is useless here. So let's say that's the problem. The next step is we need to measure that this is in fact causing the problem. And in this particular case, we can use perfstat. Perfstat is a Linux command line utility that you can use to query the hardware performance counters. In our case, we want to figure out the number of branches and the number of branch meshes. So we do that, and we get about 1 billion branches. This is the actual number of branches executed, not the number of branch instructions in the code. So while computing, we're executing 1 billion branches, and then the yellow part, those are the branch meshes. It doesn't appear to be a lot, but maybe it is. Like, it's meaningless without a comparison whether or not that's many branch meshes or not. But again, let's just assume there are too many branch meshes. What do? We somehow need to work around them. So if we don't want a branch instruction. So instead of like comparing the values, let's just jump to the correct execution code directly with function pointers. That's the idea. This is called call threading. And it's called threading. Many of those dispatching techniques are called threading. They have nothing to do with threads, right? It's a different metaphor. They're just called threading. So the idea is to use an array of function pointers. So we've got separate functions that execute each instruction. So we've got one function that executes push, one that executes add. Then we keep them all in an array. And then inside our loop, we index into that array and call the appropriate function pointer. Right? That way, we don't need to do like conditional comparisons to figure out where to jump to. We just get the address and call that function. Of course, the function itself needs to take the interpreter state by reference, right? Because we will modify the instruction pointer in it, and we want those changes to reflect back. Questions about this particular dispatching approach? Okay. So let's look at its assembly code. This is the main loop. In the middle, we are getting the address from the array. So this is the indirect instruction that I mentioned in the addressing mod. So x20 stores the base address, and we're indexing it with w8, which is the opcode. Then we're calling that. Before that, we need to prepare the arguments. The arguments are references. References are pointers. And so the actual instruction pointer and vstack pointer, they're stored somewhere in memory. In this case, on stack memory, and we're setting their pointers by computing the offsets. Then we can call them, and when we return, we need to reload the next opcode somewhere from the location we have stored in memory, compare it against the exit instruction to know to exit the loop, and if not, we jump back to the beginning. So now we don't need to do like the linear search or binary search to figure out where to jump, and we are a lot faster. So new benchmark results, in green, we are a lot faster. Okay, it's significantly slower, except not actually, because this is a really bad graph. I should have used like a proper tool to create the bar chart. Instead, I just went to some arbitrary website, plugged in the numbers, and got this bar chart. If you look closely, and in the last rows you can't, it doesn't actually start at 0. It starts at 450 milliseconds. And the switch statement takes 460 milliseconds. So it appears that we are significantly slower, whereas actually it's just 75%. This is how the bar chart looks correctly, right? We are about 75% slower if actually start at 0. So watch out for that. This is like a really common technique to create misleading graphs. So why are we slower? The answer is memory overhead. What do I mean by that? This is the do execute push function if it were to take everything by value. Again, I've shown you the assembly code in the switch again. We're loading, we're storing, we're adding. Quite simple. This is the same function if we are having call by reference. Now we don't get the arguments as arguments, but as pointers to the arguments. So before we can load the next byte, we first need to load the location where the vstack pointer is stored. And then we can load the actual byte. And before we store it, we first need to store the vstack pointer, and then we can write into it, and then we can store the new one back into the vstack pointer. So we've got this extra indirection in here because CPU can only work on register values. So we repeatedly need to reload them from memory, which is slow. Okay, can we do better? Can we do the same approach, but without the memory overhead? This is where token threading comes in. It's also called indirect threading. It also has nothing to do with tokens. It's such a confusing naming scheme here. And the idea is that instead of having an array of function pointers where we call a separate function, let's just jump to the same location within our same function. This is possible with a GNU extension computed goto. So C++ has a goto statement. You probably know that, and if you didn't, I didn't tell you. So goto statement. We can, normal C++ code, we can label a statement, and then we can go to that label. It's useful if you want readable control flow. And computed goto adds two things. We can take the address of the label with double ampersands, because of course. This gives us a void pointer, and then we can go to that label by dereferencing that address. And yes, we're dereferencing a void pointer. It's just part of the syntax. So we can dereference a void pointer and go there. And now, essentially the same approach, but instead of an array of function pointers, we have an array of labels. And then inside our loop, instead of calling a function, we're getting the address from the array and jumping there. And after each execute push, for example, we continue by going back to the beginning of the while loop and continuing on with the next iteration. And the generated assembly code looks very similar at its core. So we get the base address, we get the opcode, we get an index into the array, we jump there, and then we jump back to the beginning of the loop. Except the compiler actually doesn't generate this sort of assembly code. The compiler looks at that and sees, OK, so after I have done push, we're jumping to the beginning of the loop. And then we're jumping somewhere else. Let me just jump to the correct location directly. Right? Why go to the immediate step? So it duplicates the code at the top and pastes it after I do execute push, do execute add, and so on. And this has another advantage, that we can combine the load of the opcode with the increment. So we can increment the instruction pointer to the next and load this opcode in one instruction. So it looks like so. We only have a single jump at the beginning to bootstrap, and then after each execute push, we're loading the next opcode and incrementing the instruction pointer at the same time, getting the address, and just jumping to the correct location. And this is also where the name threading comes in, because the control flow now is completely not obvious, right? We're just jumping between the function all the time. It sort of like forms a thread or something. I think that's the metaphor. And because the compiler is generating assembly code like that, it's sort of like the canonical way to write it in C++ as well. So this is the same thing in C++, no loop. We have an initial goto to bootstrap, and then a separate goto after each single instruction. So this is token threading, and it's essentially the same thing as with functions, just with computed code. So let's benchmark that approach. Are we faster? We are. And this starts at 0. So we're now about twice as fast compared to the switch. But note that if you look at the assembly code, all those instructions start with a B. Those are branches. So we're still doing branches. So what about the branch misses? Let's measure. At the bottom, we've got significantly fewer branches, because we're only having one branch after every instruction instead of the binary search, and we also got fewer branch misses overall. Both percentage-wise and in absolute values, we've got fewer branch misses now. So why do we have fewer branch misses? Well, now we got duplicated branches. So with the switch, we've got a single dispatch at the top that was shared for all instructions. This means there was a single location the branch predictor can be used, and it can only learn about what's the most common instruction. But with threaded dispatch, we've got a separate branching point after every instruction. So they can be separately predicted, and the CPU can learn, for example, okay, after a push instruction, we're having a sub instruction. So we predict accordingly. And after a sub instruction, we're having a return or something. Right? So we can learn what's most likely going to follow each individual instruction, and we get better branch prediction. So that's good. Now we want to figure out exactly what's slow. So let's say we want to figure out what's the most common expensive instructions in our program. And for that, we can use a sample-based profiler, for example, perf_record. It runs the program and frequently asks the CPU, hey, what function are you currently in? And then we can get the most expensive functions in our program. And it helpfully tells us that 99.85% of our runtime is spent in dispatch. That's not really useful. This is actually interactive. Like if you run it in the command line, you can then go to dispatch and get the assembly instructions inside dispatch annotated by performance. But it's really difficult if you just want to figure out, okay, what's the most expensive instructions. For that, we really need separate functions, because perf_record and perf_report work on a function basis. So can we combine the separate functions for executing instructions, but without the memory overhead? And we can using tail calls. So the idea is to go back to separate functions, as we did with call threading. But now instead of passing everything by reference, we're passing things by value. And we're taking the idea from token threading, where each function now calls the next one. So after we execute the push instruction, we're calling the next one with the new values. Now we don't need to pass everything by reference, because we're not returning to our caller. We're passing the new values along to the next one. Of course, this is a function call. And a function call means that the CPU needs to remember where it came from. So it needs to push the program counter, jump to the label of the function, and then return, pops the program counter, and jumps back. This means that we start executing dispatch, we put its program counter, and jump to the first instruction. So after we're done finished executing, we push the program counter and call the next instruction. After it's finished, it jumps to the and so on, pushes the program counter until we finally reach exit, at which point we're done and we do a return. This pops the program counter and jumps back, which returns, pops the program counter and jumps back, pops the program counter and jumps back, and so on until we're finally back at dispatch. So if we try this technique, we're going to get a Stack Overflow, because every single instruction is a function call, and we've got executing like millions of them in this little piece of code. But it's a bit silly what we're doing. Like, so for example, the duplicate instruction, it calls the next one, which is an add or something. And then, but to do that, it needs to remember the program counter. And when add returns, it goes back to the duplicate instruction, and it immediately goes back to its caller. So why did add bother coming back to dup? We are just going back to our caller. Add should just skip us and go back to its caller. That's the basic idea. So when we got a function that ends with return foo, we don't need to come back to us, right? We can just forget about us. We are just going back to our caller. So we just jumped to foo instead of calling it. This means that dispatch is an actual call, so we push the program counter, but then we just jump to the first execute. When it's finished executing, it jumps to the next execute, do execute push. When it's finished executing, it jumps to the next one. We don't keep incrementing the call stack. So finally, when we reach the exit instruction, we do a single return. That return will look at the program counter that's on top of the call stack, which is the dispatch one, and so it immediately jumps back to dispatch. And then nothing was lost. We don't need to follow the chain of instructions at the end backwards, because they're just going back to our caller. Just go to the top level immediately and skip all the intermediate things. This is called a tail call, right? Because we don't need to come back, we just jump and forget about us. And compilers can do that for you. It's tail call optimization. But we can't really rely on, like we absolutely need that optimization, right? If we implement the interpreter like that, we can't run it in debug mode, otherwise we would have a Stack Overflow. And this is where my favorite C++ attribute comes in. It comes from Clang, it's called Clang must tail. And we can use it to annotate a return instruction. And then Clang is always going to generate a tail call, even in debug mode, even with optimizations disabled. And it will also give us an error if it can't do a tail call. So we can rely on, if the program compiles, we're getting a tail call. For example, it can't get a tail call if we're having code after the return statement, like implicit destructor call, right? We're not going back to our function, so it can't issue call a destructor to destroy our local variables. So this is a really useful attribute. And with that, we can just write the interpreter like that, but annotate everything with Clang must tail. And now we generate assembly code that looks almost identical to the previous one. So we still got our labels, we still got the arrays, we're still jumping there. The only difference is that now the actual address of the table needs to be recomputed. But otherwise, it's exactly the same assembly code as with the previous approach without tail calls. The difference is now on a function level. And so the actual performance, like, it's almost identical. In this particular image, it's faster because I picked that image that way, but actually, if I were to report the actual noise, like, they are identical, right? It's no difference in execution time. Just picked one that underlines my message, and you shouldn't copy this benchmark results, you should run your own benchmarks. And because it behaves the same as the threading approach, it also gives you almost identical branch methods. I don't know why it's actually like slightly different amount of branches in there and branch methods. I have no idea, like CPUs are black magic, I don't know what's going on there. But crucially, because we're now having different functions, perf works. We can ask perf what are the most expensive functions, and it tells us that 16% of our runtime is spent doing push. So we might investigate optimizing push further. So that's really useful. Questions about this technique? Yes?
Any chance to get this working with MSVC? Okay, let's repeat that. Yeah. Everyone can hear it. Is there any way to get set working with MSVC, which has neither GNU, go to label, and must tail call?
So as far as I know, Clang must tail, like the must tail sort of behavior is only available in Clang. There was in the beginning of the year, there was a discussion about the GCC mailing list, but they need to support esoteric targets where they can't really do tail calls. So my current strategy is like the projects that use them need Clang, right? It's a really cool technique, but unfortunately it only needs Clang. Okay. So, really great so far. Let's talk about the register keyword. So the register keyword comes from C, and it tells you to please compiler, please keep this variable in a register. This is useful as an optimization because, as we've seen, if you keep things in register, they are faster, right? Of course, modern compilers will do that for you, which is why C++ still has it as a keyword, but it has no meaning in C++. Except they don't, right? It's an optimization. So sometimes the optimizer doesn't really want what you're doing. And you don't need to take my word from it. You can take Mike Pal's from word. So he's the author of LuaJIT, which is a just-in-time compiler for Lua, but it also comes with a bytecode interpreter, similar to one we are doing, but his is written in assembly. And in this email that link is also and yet in the resources, he talks about why it's written in assembly. So he says that we can use like a direct or indirect threaded interpreter in C, just they're doing with computed Go too. But the disadvantage is that like the register allocator of the compiler doesn't really understand that. And in particular, there's like no way to say that we want the same register assignment before each Go to. So for example, the instruction pointer should always be kept in the same register. Even if you're doing push or if you're doing add, it should be kept in the same register so that we don't need to move it between registers just because we jump somewhere else. And there's no way to express that, the compiler. So let's talk about calling convention. When we have a function call in assembly, we're just jumping to an address. How are the arguments passed? This is what the calling convention dictates. And it states that on 64-bit ARM, the first 8 registers are passed in the first 8 arguments. Very straightforward. So whenever we call a function, the compiler will put the arguments there, and then the function knows where to find them. This means that by using tail calls and functions, we are forcing a particular register assignment. Right? Because the instruction pointer is the first argument, it will always be in x0, right? As we can see in the assembly code. x0 maps to the instruction pointer. So when we then call a function like execute push, the instruction pointer will be in x0. Then we're doing something, and at the end, we're calling the next one, which has the same signature. So IP must also must again be in x0 for the call. Of course, the compiler is free to like move it around in between, but that would be silly, right? So essentially, we're forcing the compiler to use a particular register assignment. This means that if we want to ensure that something is kept in a register, just pass it as an argument to the function. We can force the register allocator to do a good job. Mike Pell's email continues listing advantages for writing things in assembler, like keep the fixed register assignment, but we can also do that, right? As I've shown you, we can keep the fixed register assignment. And then for slow paths, like if an instruction has a fast path in the common case and then sometimes need to do something slow, we can move them elsewhere to help with iCache density and so on. So let's investigate that. This is a silly instruction with a slow path. So we want to print 42 if the top value is 42. We can then benchmark this instruction by changing bytecode for FIB35 to start with a print 42. In this benchmark, we're never going to printing 42 because it will always like check the argument, and the argument is always 35 or less. So we're never going to print anything. So the performance should know different, and it shouldn't be significantly faster. It doesn't start at 0. It's 4 milliseconds slower if you have print 42, not like 8 times as slow or something, right? Really watch out for those. So it's 4 milliseconds slower for print 42. This isn't much, but it's a bit sad because like we're not printing anything ever, right? We're just paying 4 milliseconds for a branch that's not taken. What's going on? Well, if you look at the assembly code for the print42 function, it's really obvious. Like, what's all this crap? So at the bottom left, you got a call to puts, right? We're calling puts. That's okay. But to call a function, we need to set x0 to the string. But x0 is our instruction pointer, so we need to save it somewhere. So we save it a couple of instructions above in x22. But x22 might have a different value already, so at the beginning of the function, we push x22 on the stack. And then when we end the function, we load x0 back from x22, and we also load the previous value from x22 from the stack. And the same is true for the other argument registers, because puts might internally call another function which populates those. So as soon as we call a function, we need to save all the registers, right? And this adds overhead. And it's a bit silly because what the compiler generated here, because it always saves all the instruction registers, even if we never end up calling puts, right? It does it unconditionally, which is a bit unfortunate, but simply like the compiler doesn't know that we are never going to call puts, it doesn't optimize for that. It knows that as soon as we call a function, we need to save all the registers, so it saves all the registers, even though we might not actually end up calling the function. But don't worry, we can help it a bit. We can use a tail call. So instead of calling puts directly, we are just tail calling to a different function which calls puts unconditionally. Now the doPrintImpl, this calls a function, this is slow, this generates a lot of spilling. But the initial function never ends up calling a function, right? It only tail calls a function, so the compiler doesn't need to save anything in any registers. So we can sort of like trick the compiler into generating the good assembly code. And we really need to trick it because it absolutely doesn't want to do it, right? We have to mark print_impl as no inline, because otherwise the compiler says, oh, that's a silly function, and just inline it above, and then generates the bad assembly again. Right? We're really fighting with the compiler here. But if we can end up winning by just slapping enough attributes on it, and then the compiler will generate the assembly we want. At this point, we're essentially writing assembly code here just in C++. But it works, and we get this nice assembly. We're getting the top value, we're comparing it against 42, And then we might jump to the print function, or we might not. And with that piece of code, we get the same performance again, right? Which makes me really happy. And this technique is like, as soon as you have an instruction that might sometimes be slow, or call another function, like you lose all performance benefits of tail calls, because then we need to save things. So this is really common. For example, we might want to dynamically grow the call stack on recurse, so we don't have a stack overflow in the interpreter. So when we reach the end of the call stack, we want to grow it. This is expensive, so we tail call somewhere else, which actually performs the grow. This is the expensive function, but it's almost never called. And then, of course, we want to return back to our caller, but we can't do that because it's a tail call, right? When we tail call somewhere, we lost track of who called us. So what we're instead doing is we're jumping back to the beginning of the function. Then we're checking the condition again, but since we've grown it, we're no longer at the end of the stack, so we skip over it and continue. So this is like absolutely non-obvious control flow, but like it's fast, right? So that's the price you have to pay. Like as soon as you tail call somewhere, then you tail call back to the beginning, and then you need to keep track. Like if we already increment the instruction pointer or something before we do it, and then we jump back, like this is like really difficult to remember of what you changed, and what, like it's tricky to write, but it's fast. So this was the original conclusion I planned for the talk. Clang must tail enables threading via function calls, which is really good technique. You get detailed performance tracking in perfect code. You can force the compiler to use a particular register sign by simply passing it around. But you need to remember to host the slow pass, no regular function in hotcode. And that way you can trick the compiler into generating the exact assembly you want. All is good. And then I thought, well, at the beginning I have a disclaimer that you should benchmark on the exact target hardware that you're targeting. So just for fun, let's benchmark it on my laptop. So let's benchmark it on my laptop. So new benchmark, this is a 2016 ThinkPad 13, so an older CPU, running Arch Linux and Clang 14, and as you expect, you get the exact same performance behavior. Why is Switch suddenly so much faster than everything else? Right? What's going on here? Well, if we look at perf stat, it's really obvious what's going on here. We're having significant amount of branch misses in the other techniques. So switch on top, and then we've got threading and tail calls, and they've got like almost 25% of their branch misses. Why? Well, the difference is the issue is branch target prediction. So with the switch, we've got a conditional branch, but it has a fixed target. So we're getting each individual value, right? Then we're comparing it against something, and then we might jump. The decision whether or not we jump, that might change, but if we jump, we're always jumping to a fixed location. Whereas with the jump table, we're always jumping, right? We're unconditionally going somewhere else. But the address is completely variable, right? We can go anywhere. So branch target prediction is responsible for the write code. It needs to determine where a branch is going. The original branch predicted only checks whether or not a branch is going, but branch target prediction, when you have a variable target, needs to figure out where we want to go. And that's a more complex thing, right? Yeah, they have multiple destinations, right? It's more difficult to do. And they simply, like, this is a cheap laptop CPU, they saved on that. So this has a really poor branch target predictor, which is why we've got the high number of branch misses in our code. So this is slow, right? We need to work around that. We can't use variable targets. And this is possible. We can just use a switch, right? Instead of the lookup table where we're tail calling something, we're having a switch. And then if it's push, we're tail calling to the do execute push function. If it's add, we're tail calling to the do execute add. And now we again got a fixed target that may or may not be jumped. So we get now need to rely on branch target prediction because we got fixed targets. And this means that the number of branch misses now at the bottom is like exact behavior as with the switch. Lots amount of branches because we're doing the binary search, but few number of branch misses. And this makes it faster, right? We're now similar performance to switch. I thought, hey, that's an even better conclusion. Because it turns out, just trust the compiler to do the dispatching for you, it knows best. Right? I've just wasted 40 minutes of your time. Just write a switch statement, everything's good. Except not really, because that particular code, like if you have a good branch target predictor, like the jump table is fine. Right? It can be predicted, it is faster. And I've also lied about you. Because this isn't the actual generated assembly for a switch. This is the actual assembly generated for a switch. And you've seen enough assembly code to recognize that's a jump table. So no, the compiler doesn't know what's best either. It generates a jump table, which is bad on my CPU, right? It has no idea. It only generated the binary search after I nicely asked it to not generate a jump table because I wanted a different dispatch implementation to compare it against in benchmark results, right? So by default, it will generate a jump table, and there's a flag like f no jump tables or something, and then it will generate binary search, which is what I need on my laptop. So now, the compiler doesn't know best. You need to run your own benchmarks, own optimizations, look at the assembly code, look at the branch methods. So now I want to talk about 2 more advanced dispatching techniques. So we've got token-threaded dispatch. And the idea is that the instructions are essentially like tokens, like integer values, and then we index into an array. This might be an array of labels or an array of function pointers, and then we might use computed go to or tail calls, right? It doesn't make a difference actually in the assembly, same approach. So why not cut out the middleman? Instead of having a table, and we index into the table and jump there, let's have the opcode be directly the address where we're going. So instead of an enum, we now got the address of a label or a function. And then, after we're done, we simply go to the next address or call the next function, right? So the bytecode operands themselves are no longer enum values, small byte integers, but full 64-bit addresses. And then we don't need to do the array lookup, we can just immediately jump there. And on the assembly code, right, this generates really tight assembly code. We just go there, we get the next one, and we go, right? Really good. So the best dispatch code so far, right? Because it's like, if we want to go somewhere, we just go there, right? Can't get better than that. But the downside is now the opcode is 64-bit instead of 8-bit, right? This makes it bigger. We might run into issues with cache prediction. We need branch target prediction, so this approach is slow on my laptop. And it makes it really trivial to do remote code execution exploits because we're now jumping to a value that the caller gave us, right? There is no check. So we might jump anywhere in our program, which is like not ideal. And I haven't presented the benchmarks because if you want that, do their own watch out for the safety implications. But on my laptop, like it's slow because branch target, and on my M1, it doesn't really make a difference, right? It's within the noise from the other technique because the array overhead isn't that much, and the bigger benchmark might cause issues there. So this was the best dispatch code so far. But let's rethink the approach. For example, we might want to call push1, push2, and then add. So we want to execute the assembly code for push1, and then the assembly code for push2, and then the assembly code for add. So let's just insert the assembly code for push, insert the assembly code for push, insert the assembly code for add. Right? This isn't just-in-time compilation, we're sort of just copy and pasting the various assembly code. A just-in-time compiler would, for example, be loading the 1 from memory, and it would just inline it and just directly store 1. It's just sort of a simpler way. We just know the assembly code, and we just copy and paste it around in the correct order and get the idea here. This is called inline threaded dispatch. And the idea here is that the best dispatch is no dispatch, right? We don't have any dispatching code. We just, after we've done the push, we just start executing the next push, and then we start executing an add. But the downside is this requires just-in-time compilation. So it's not available on all systems. You need to be available to, at runtime, dynamically build assembly code. And for that, I've got the actual conclusion for my talk. Benchmark on the target hardware, then optimize. Right? It's really difficult, as we've seen, like different systems make different things. But the must-tail call technique, in general, it's like flexible. You can combine it with different dispatching techniques. You get full control. You essentially get assembly code without writing it. Full slides, source code is available at that URL. Follow me on Twitter while that's still a thing. And if you're interested, I'm currently writing a C interpreter live on YouTube, so subscribe there. It's a bytecode interpreter using the dispatch techniques I presented to you. Thank you. I now have time for questions. Yeah. There's a microphone coming.
So you know, if you do an immediately executed lambda, yeah, could you do that instead of a tail? Well, I mean, can you annotate that with a tail call and then do that, and then it would make the bit where you're sort of going off over there and coming back a bit less grim? Does that actually work?
You mean like yeah, I mean I have time. So in this code, instead of returning what we would use an immediately.
Yeah. So grow call stack. You put that inside a lambda, which you annotate with well, you make it cold, take it out of line, Will the tail call work in that context?
So what you can definitely do is you can the tail call applies to return statement, right? That the return that calls a function, and that function can be immediately invoked lambda as long as it doesn't have a destructor that does something. But yeah, like you still, I mean, then it's a bit more obvious that because you see the code, but at the end you still need to return back. What I haven't tried is to mark a function as cold and call it and see whether the compiler then does the exact assembly immediately.
I mean, I think it does do that. I think if you if you got an immediate, I think it just will go off to there and then come back. I'm not absolutely sure. I've looked at this in connection with like optimizing throwing exceptions.
Yeah.
So you take all the stuff for preparing the exception, take it all out of the hot path. And I can't remember if it if it messes about saving stuff down to the stack before it does it. But yeah, I was just curious.
Yeah, like it's something. I thought like it just depends where the functions are placed in memory and whether they are predicted and things like that. I don't know whether that actually affects like the register saving code if you have a cold function that you might or may not call. It might be it might be smart. Like it should be. It definitely should. Right? Because like there should be some way to prevent this sort of behavior when we know that this is. So just saving that inside the branch, doing the save there.
But there's another thing on Intel architecture. Interregister moves are free because they're done at the instruction decoder stage.
Yeah, so definitely the moves themselves, they are not the issue. The issue are the stores and the loads at the beginning and the end of the function. Yes. Right in front of you.
I really like Mustail. Is there a paper to standardize it sometime?
I don't think it's ever going to be standardized because the standard doesn't know about tail calls. Right? There was a coroutine proposal that relied on tail calls. Sort of like at the first step we need to formalize tail calls, and I don't think that even that part didn't went anywhere. So yeah, it's like we are forcing the compiler to generate assembly code. It's highly specific stuff. The standard isn't. Right? I would be happy if GCC supported it, right? Then I would be happy. But
yeah, I mean, it's just a shame to not standardize it because here you're right. It's a bit niche, but there are cases where you really would like to use tail calls. Yeah. But it would just blow your stack up. So you have to rely on optimization and
yeah.
So anyway, thanks.
Maybe more a comment than a question. Have you considered, instead of making dispatching faster, making dispatching a lesser occurrence by fusing opcodes?
So this, like if you're writing a real interpreter, for example, I have time, so I go to the slide. This one. This one, if you see code like this, so in this particular case, we now push is modern. And like, if you look at the bytecode, we do push 1, we do push 2, right? It might make sense to add dedicated opcodes for push 1 or push 2. Or we're doing like a push 1 sub, so it might make sense to add a sub 1 or fuse the instructions together. This is also optimizations you can do. I haven't I'm using this technique in a bytecode interpreter I'm using. It doesn't make sense for the talk, obviously, because it's about dispatching. But like to do that, you really need like a sequence of real-world programs to figure out like what are the actual common instructions, which is why I'm writing a C interpreter that uses that bytecode. So I can get real C programs, figure out what are the expensive instructions, and optimize accordingly. Like you really need data, and not the micro benchmark that. Like you can make every benchmark as fast as possible, like, and then that particular function is fast. Like I can add a fib instruction, and then we're just, right? Yeah. At the very back now. Exercise.
So why not just write it in assembly rather than force the compiler?
So why not? Like at this point, we're essentially writing assembly code just in C++. The issue is, in my particular case, I'm programming on this laptop, which is x86, and I'm programming on M1, which is an ARM architecture, so I need to write 2 interpreters at the same time, which is just a lot of work, right? So it's like, this is more portable than writing it in assembly.
Except you need to benchmark on the target architecture.
Yeah, except I need to benchmark on the target hardware. Yeah, but just benchmark is like different than writing assembly code. I actually, I will end up writing a JIT compiler sometime anyway, and by that point I can write it in assembly code, but for now, like, it's quicker to prototype something and you get like most of the performance, as I've demonstrated. Well,
thank you.
Argued.
Hi. Would there be a benefit of just writing one function with many go-tos instead of function calls and lots of proprietary attributes which don't work on every compiler?
I mean,
like writing one function and keeping, being careful that you only use variables and primitive variables, and no destructor can be not called or something.
I mean, that's that approach, right? We've got one function that contains a bunch of go-tos. This is like the usual token one. The main reason I switched away from it is actually to get like better perf record, and then I learned about the other advantages. Like, it's sure you can also use the technique. Like, this is sort of like the traditional way of how you write. Like, the literature says if you want to write a fast interpreter in C, you use computed go-to, right? And then everybody uses computed go-to without thinking about it. I didn't come up with the tail-call technique, by the way. I just
Yeah, hi, thanks for the great talk. This is not a question, this is rather a comment.
Sure.
I can only add to your point, if you really want to have the ultimate performance, you can't be generic. You have to know your precise hardware and its characteristics, and you have to know your compiler. I work in the automotive industry, and we have weird embedded system processors and weird outdated compilers, and it's cool what Clang can do these days, just that we don't have it. And at the end of the day, you have to live with what you have, and you can't be generic, or you're suffering from performance issues. So that's the point. Thanks for adding to that.
I added the slide, run the benchmark on your own target hardware, and I thought, let me just follow my own advice, and then I discovered, it behaves completely different on my laptop, right? And then I optimized, added a switch for my real bytecode interpreter to use the switch versus the lookup table based on that. So you really should do that, right?
That's a key message to the big companies who dream about having a software platform that runs on any kind of thing. Yeah, it will run, but it will not run optimal. And that's just the way it is, and you have to live with that. Thanks.
Okay. Thank you.